let's do it. My talk is about the attribute graph. And this is the system that you actually don't really need to know about if you listen to Apple, because it's always hidden and they never really talked about it. The only thing we always saw was these errors, right? If you're writing SwiftUI, you got like the AG errors and something went wrong, but we're not supposed to know about it. It's an implementation detail. I think it's very important to know about, because this is how SwiftUI works. And I think especially today, in the age of LLMs and everything, and AI and all of that, we need to understand what's happening, right? Like if we don't write the code, but like coworkers do, or LLMs do, or whoever does, right? We still need to be able to understand and reason about it. And the attribute graph is sort of the implementation detail. Most of the time, you actually don't really need to understand and know about this. But if you have a problem, it becomes very important. And especially once you start to build apps that are a little bit more advanced and you get performance problems, it's even more important. And I think it's always very helpful to understand the fundamentals below, and then all the other stuff will become simpler. So let's see if we can run this. This is just a Hello World app. I can see the simulator, and now you can as well. Okay, so we're going to just build a little app and see how that works with the attribute graph. Let me move this. Move this. Okay, so we're going to build a little counter. And then we're going to create a struct counter. This is a view. It has a body. And in here, we want to have a button with the value. And when we tap it, we want to increase the value. And we can now add a property for the value. So we could say var value equals 0. And this is almost a correct SwiftUI program. It's not quite right. It says something about mutable. And the way to make this work in SwiftUI, I think if most people that have written SwiftUI will notice, of course, we have to mark this as a state property. And now I think it should run. So let's see. So we wrote a content view and a counter. And we can increase the dynamic type size. So we should be able to just tap it, and it increments. So I think this is kind of magical. And if you don't really think about it, it sort of looks okay, and it works, and whatever, right? But I think it's very important to understand how this actually works. So how the views that we write get interpreted and executed. And this interpretation and this execution happens in the attribute graph. And I think if we set a breakpoint here, for example, on line 14, and tap, we should expect that the breakpoint hits. So we tap it, SwiftUI updated the state property, and now we hit our breakpoint. This is expected, because every time the state changes, the view updates. So let's continue. And now it updated. This is also the magic of SwiftUI. For those that have written UIKit or similar code, you know how hard it is to keep your state and your views in sync. It's the hardest thing to do this correctly. And this is why people came up with stuff like MVVM and all the other architectures that we had in the UIKit days. SwiftUI actually completely solves this problem. Your UI and your state will always be in sync. And I think that's very, very impressive. And mostly we don't really think about this. Now, one naive way to do this is every time any state changes is to re-render everything all the time. But that's not what's happening. So let's set another breakpoint here in the content view body, and let's run this. So we can run it, and we hit the breakpoint. So let's continue. We hit the second breakpoint in the counter body, and then it renders. And now is the magical part. If I tap it here, it only hits the breakpoint in the counter body. So it's kind of efficiently only updating that counter, but not the content view. And so you think, well, OK, that makes sense. But we can make this more interesting. So let's add an H tag around the counter. I say text value and run it. So now what happens is we have our text and we have our number. So we got the breakpoint, continue, continue. If we tap the number, we hit the first breakpoint inside the counter. What's going to happen is the moment I press next, it will actually re-render, and that label with the value, if you watch it closely, you will see it move a little bit. Did you see it? I'll remove the breakpoint. Or actually, let's just tap it again. We can again see there's no breakpoint hit in the content view, only in the counter, and yet the label will move a little bit because of the width of the digit. So what's happening here under the hood is the H tag is actually doing a relayout pass. And so if you think about it, that's really smart in some ways, right? Like SwiftUI is very efficiently only executing the body of our counter. It's relayouting the H tag without executing the body of our content view. So there's all kinds of efficiency at work here that we never think about. And I think it becomes important once you start to reason about performance, to be able to reason about why views are updating and why the body is executing. Okay, so let's make it a little simpler still. I'm going to remove the counter here and just do some text. See if I can still remember my Italian. And let's move the breakpoint to here. So this should just hit once to render the first view. Okay, so that works. What we can do is actually change the dynamic type size. So let me make it smaller. And the breakpoint never hits. So what's happening is SwiftUI is reading from the environment, reading the dynamic type size, re-rendering our label without executing our code. It's even if you change the appearance, that works without executing any of our own code. This is all sort of magically really efficient. And it's also interesting, we can see something like this. If we set the foreground style to red, execute it again. And now let me enable the breakpoint. Even this will automatically update. So let me add digital color meter. So let's see if we can see the values here and now change the appearance. I don't know if you can see the values change in the color meter. So the numbers don't matter, right? But the fact is that as we change the color scheme, SwiftUI will resolve this red to a different RGB value depending on color scheme, on the user settings, like the contrast stuff and all of that. So all of that happens automatically below the hood without us thinking about it. And the attribute graph is what powers this. So now we're going to make it a little bit more interesting. Let's see. Because I brought a virtual assistant, an LLM, to help me explain this. Let's see. So it's called Klaus Code. And it's a new hidden assistant in Xcode to help you understand many things. So I do hope it's a little bit more efficient with water than the current LLM. So we can pick, let's pick SwiftUI. That's what we're here for. So let's pick SwiftUI. And apparently it's a little bit weird because it still has all these swimming analogies. It tries to really, I try to tone it down, but it's still always doing the swimming analogies. Okay, so can we implement a simple content view with a counter? And I hope the network is fast. Okay, my training data is not just pool lap times. There's also a lot of SwiftUI. Okay, so we have our content view and our counter. So this is basically what we wrote before ourselves, right? So now let's see if we can get that counter to work. What would the counter look like? It's not very fast. Okay, so here we go. And this is basically what we wrote before, right? Like it's the most simple thing you could write in SwiftUI that's interactive. We have our content view and a counter and a button. And let's see, can we run this code? How do you want to run this? So we can choose the Mac app or we can use the class code simulator. I think I want to live on the wild side. I hope this will work. So it's thinking. Okay. So we got something that looks like a simulator. Let me close the old one. Oh no! Now it crashed. we need to quickly start again. Let me quickly jump through the simulator. We can go through the old transcript. Okay, here we go. So it vibe coded the simulator, and we have it running here, and we see the number 0, and we can tap it, and the button increments, right? So it's very boring in that sense, but it's the same app, and it runs the same way, just in the terminal, like all modern UIs these days. I'm glad they got on board with that. Okay, what does the attribute graph look like? Okay, so this is where it starts to get interesting. So it thinks a bit, and I hope it can draw something for us. Okay, so we got an interactive diagram that contains the attribute graph for the content view. Let me make this a little bit wider. I hope it doesn't crash again. Okay, so we have our content view. Here we have our body and we have our counter. And we can see at the bottom there's shortcuts for invalidating and recomputing. And this is how the attribute graph actually works. It uses a 3-step algorithm. So the first step is that anytime something changes, let's say a state property or the content view or something else, that gets invalidated. So we can try that with the I button. And now we see the content view has a red outgoing edge. The body and the counter are marked as gray. And so the first step that happens whenever a node invalidates is that it marks all the outgoing edges as red, all the direct edges. So in this case, there's only one outgoing edge, and that's marked as red. This means that the edge is invalid. The content view has changed. The second step in the attribute graph is that all the descendants, direct or indirect, are marked as potentially invalid. And the reason is that SwiftUI will not re-execute everything all the time. It only wants to do that if absolutely necessary. So everything down below will be potentially invalid. And that's what we see here. The body and the counter are slightly gray. So those are the first 2 steps, marking all the edges as red, and then everything down below as potentially invalid. Then at some point, the system requests a new value. So in this case, let's imagine it requests our counter. So we can recompute that, and then it will see, okay, it's going to look at the counter and bring the dependencies up to date, so it goes up in the graph. So that means it needs to bring the body dependencies up to date, because that was gray, and the body has a red incoming edge. And something changed. So SwiftUI re-executes the body changes, so again, it marks everything down below as invalid, and it has a red outgoing edge. Then it hits the counter, it reevaluates that, and then it's done. So this is a super, super simple example, but everything works like that, even the really complicated attribute graphs. So let's see, what does the attribute graph look like? Because we want to also have this counter implementation in there, right? When we also include the counter. So let's see if it can do this. You never know, right? It's always a bit of a guessing game with the LLMs. Okay, here we go. We have a content view, a body, and a counter, just like before. And now we can see something else that's very interesting. A state property in the attribute graph doesn't have any incoming edges. So in this case, the way I visualized it here is that everything, all the information only flows down. So the state property, it has an outgoing edge going down, but it has no incoming edges. The body of the counter is actually dependent on both the counter struct value as well as the state property. So if somehow the content view produces a new counter struct, the body is going to re-execute. But also if the state property changes, the body is going to re-execute. And then finally, the button is in there. So let's play that and invalidate the state property. So we can see now the state property, the outgoing edge became red, everything down below became gray, and we can recompute this. So let's request a button. So it's going to bring the button's dependencies up to date, backtrack through the graph, the body dependency up to date, and the body has two incoming edges, the counter and the state property. One of them is red, so the body needs to re-execute and marks its outgoing edges red, and the button needs to re-execute. And this is how everything can update without executing the content view. So the system is really smart about this. So let's continue a bit further. Can you add an H tag to the content view and include some text? So this should show us that behavior where the attribute graph is responsible for relayouting the H tag without doing any work inside the body of our content view. So it's going to do this. It's going to generate a new content view. And this is exactly like we just wrote ourselves. So let's see if we can see the attribute graph. First, we can run this. And now we can see that same simulator again. We can change the value. And let me go to 9. So hopefully, if I press enter again, it will go to 10, and everything will move a little bit. Perfect. So we did have that H-tag layout pass. So let's look at the attribute graph. I think this might get a little bit messy. Okay. Oh, yeah, it's thinking for us. So it removed the borders in the graph. I guess we don't have all that much space in the terminal. So we have our content view, we have our body, and our H tag. And the H tag has two children. The text is the first child, and the counter is the second child. And basically what we see here from the counter and to the right and to the bottom, that's the same graph as before, just without borders. We have the state property, the body, and the button. So if we invalidate the state property and then recompute the button, it seems like it works, but this does not explain how everything got laid out again. So there's something missing there. It seemed to work, but there's no explanation for that behavior of everything relaying out. So let's ask it. How can the H tag relay out when the content view body is never executed? That is a great question. It's done through layout computers. That doesn't really help us. It's so hard to work with these things, right? What is a layout computer? So I wonder what it comes up with. Think of layout computers like lane dividers in a swimming pool. They keep everything in the right position. Enough with the swimming analogies. What does a layout computer do? We need to be very clear to these things, right? Look, and they don't have a personality. They're not offended if we tell them straight up and be direct. So let's hope it listens. It's thinking. The layout computer is responsible for positioning and sizing a view. So that makes sense. So I imagine like a layout computer might there might be a layout computer for the text, for the button, maybe for the H tag. Let's see what it says. Please tell me more. Okay, let me read this to you. Leaf views such as text have layout computers. Okay, so that makes sense. Leaf views such as text and probably button. Layout modifiers such as padding or containers like H tag also have layout computers attached. And this also kind of makes sense, right? Because the H tag is responsible for positioning all these views next to each other. And padding is kind of similar, right? It's kind of like an H tag, but just with a single child. And so apparently there's a bunch of things in SwiftUI that have layout computers. Can you change the attribute graph to include the layout computers? Okay. This is very complicated, especially in a terminal, but let's step through this together. I think it will make sense. We have, just like before, our content view, our body, and the H tag. In the H tag, it's not very clear here, but it has two children, the text and the counter. And here for the counter, we can see that same subgraph like we had before, the state property, the body, and the button. And now we can also see three layout computers at the bottom. The text has its own layout computer. And I imagine this thing also might listen to something like the environment changing, right, for the dynamic type size. But it has no other dependencies. It's just if the text changes, the layout computer re-executes. The button also has its own layout computer. And then finally, this is the most interesting one. So this is the layout computer for the H stack. And it has three dependencies. It's dependent on the text layout computer, on the buttons layout computer, and on the H tag itself. So this is how, like, let's say the H tag gets more spacing, for example, how it re-executes that layout computer. Or if the number inside the button changes, it will re-execute that. Because remember, all the information only flows down in the attribute graph. So let's try this. We can invalidate our state property. So now we can see everything down below, all the descendants are invalid. And if we go to our root layout computer for the H tag and recompute it and let the system request it, we can see it's going to bring that up to date. It's going to bring the buttons layout computer up to date, the button itself, the body, and then it flows down again. So that's the same process that we saw a few times now, and then it's done. And when I first saw this, it kind of started clicking for me, where it explains how everything can execute so efficiently without executing our code. The content view body is never executed. And yet the H tag is laid out again. So I think this explains a lot to me. Oh, it's thinking by itself now. I think the computer is taking over. Have you thought about showing them how the environment works? It flows through the entire app just like water. There we go again. I guess it's a good idea. Yes, it's a good idea. Grazie, Klaus. It's kind of like in swimming. Oh, nice. Almost. Okay, so what do you want to see? It asks me. Can you show an example of a content view with just some text? So we can see how the environment works. I guess these tools are pretty new still. Okay, so we got a content view with the body. We got some text, ciao mondo. And now let's run this. Okay, so we have another button here at the bottom. We can press the C key to change the color scheme. And just like before, this updates automatically without executing the body of our view. So it's exactly the same thing. Oh, it's starting to take over again. Oh, nice. So it drew the attribute graph for us. We have, and again, this is a simplification, right? So we have our content view. There's this new node called root environment. We have the body of the content view and the text. And the text is dependent on the root environment. And the root environment contains all the information that basically it contains all the values that our simulator or a device is configured with. So it contains the current color scheme, it contains the dynamic type size, maybe accessibility settings, and so on. And so what happens is when we change, for example, the color scheme, the root environment gets invalidated, and everything that reads from that root environment also gets marked as potentially invalid. In this case, it's just the text. So if we recompute the text, it's going to just bring that up to date and run it. And so this root environment and anything that depends on it is sort of threaded through the entire program, and everything that reads from it can update efficiently, again, without executing everything. So let's see, it's done now. Can you add a red foreground color? Rosso. Okay, so we got our content view, we got our text, we got our foreground style, and let's see if we can visualize this in the attribute graph. What does the attribute graph look like? Okay, so this is again a little bit more complicated, but I think we can parse it ourselves. We have the content view, we have the root environment, just like before, we have the body, and this is a little bit of a simplification, but the foreground color modifier is now reading from the root environment. So if the root environment ever changes, this means the foreground color will get invalidated. It produces a modified environment. So let's say that the root environment changes, the foreground color modifies the current environment, puts the new foreground color inside the values, and so the text reads that modified environment. And so if the root environment, for example, if that changes and it invalidates, then we can step through the graph again to recompute everything. So the text will get brought up to date, the foreground color will get brought up to date, it has an incoming red edge, so it changes, and it produces 2 red outgoing edges. Then the modified environment gets brought up to date, so as it executes, it also produces a red outgoing edge, and finally, the text re-evaluates. And this is how that kind of works. So, this is, of course, not the full story yet, because, for example, how does the system know to evaluate which nodes? Like, how does it decide to evaluate, let's say, the text node? But that's also like one more thing that's built into the attribute graph. And so the attribute graph is not just there for rendering views, it does a lot more. Let's see if it can tell us about this. Do you have any more pointers to learn more about the attribute graph? So while it's thinking, maybe we can, well, let's see. Okay, oh yeah, there we go. So there's a bunch of pointers here. And we can talk about the pointers in a second. So the attribute graph is responsible for rendering our views. So that's one of the outputs. It's called the display list. And in this case, there would be a display list just for the text. In the previous example, where we had the text and the button, there would be a root display list that contains both the text and the button. And this display list is re-evaluated every single render loop, every single frame that gets rendered. The other outputs are, for example, the accessibility tree. So you can request, or the system can request an accessibility tree, and it also contains all these dependencies. Yet another output of the attribute graph is gestures. And so all of that also automatically updates, and we never need to think about this. And to go back to the beginning, the thing that the attribute graph gives us is a system that really efficiently executes our code, updates our views, updates the gestures and the accessibility tree without us having to think about these updates. And understanding how this works and how this can be so efficient, I think is very important the moment you start to build more advanced apps. I think we should leave it at this. I'm very happy to take questions, even complicated ones. Like let's try it. If I don't know the answer, I will say so. There's a lot more to talk about, so I'm really excited to hear what you think and what questions you might have. Thank you.
One, two. Okay. Questions? Arcadius has a question.
Oh, 1 sec, they will bring you the microphone.
Yeah, the microphone is coming, Arcadius.
Hello, thank you for an unusual talk. I'm really happy that I could listen to it. I have a question, because you were talking about the layout computer, and my question is how the layout computer can evaluate, let's say, the size and so on, the position of controls which have dynamic sizes like lazy V stack, lazy H stack, lazy V grid, and so on.
Yes, so I think the layout computer for something like a lazy V grid will need to make a guess about the heights, so it probably depends maybe on the first few rows. I know nothing, right? Like, this is all guesswork, but I think it makes an educated guess about the height of the rows, and as you scroll, it will evaluate more and more and more rows in the lazy V stack, and it will add more and more information and maybe make a better guess. I've never tried to implement that, but yeah, I think that's how it works. So probably it depends also on the children's layout computers, but I don't know. It's a great question though, and now I want to figure it out.
Another question? There are two of us walking around.
There's one over there.
Oh, okay. Coming to Max for after.
Hi, thank you for this amazing talk. I wanted to ask you about the warnings that we see sometimes in the console of Xcode, something that tells about attribute graphs. How do you solve? How we can solve them?
That's a great question. How can we solve these warnings? So. I don't know all of the warnings. So if I get an attribute graph warning and it's one specific kind, I can solve it. All the other ones, I'm also lost. So the one you can solve is around preferences. So what can happen is, we saw the graph up here, right? And we saw how the information only flows down the tree. If you want to model something like preferences, you have like information that's synthesized from the leaf views and goes back up the graph, and so that sounds like a cyclic graph. And I will promise you that the attribute graph is not cyclic. It's a directed acyclic graph. Now, what happens with a preference is, at some point you hit an on-preference change, and there you can modify some state. And what that will do is it will modify the state. It will re-execute everything that's invalidated, and maybe that triggers another on-preference change, right? And it modifies the state, re-evaluates, and this can be a loop. And so if you try to measure something and then change your preferences, and then like you measure again, stuff changes, you get these cycles, and it says something about cycle detected. And this is something that you then need to think about and see, okay, can I break that cycle? Is my state changing, also changing the way my measurements are recorded? And so you have this, for example, let's say if you do something like, if you do a relayout, the moment something changes, and then you measure that relaid out view, and that triggers another state change, and so on, and so on, and so on. So that's basically the only one I know how to solve. I think the attribute graph warnings have gone away a lot. I did run into one a few weeks ago, and I'm lost as to how to solve it. There's, I think, a new debugger where you can see some of the attribute graph, but it's really, really complicated. So let me actually show you something. I think I can pull this up here. So this is just a simple Hello World app, the attribute graph. And let me zoom in. Wait. Oh, you cannot see this. I wanted to pull this over. Okay. So this is a simple Hello World app. And I think it's just text and a foreground style or something. We can see a lot of interesting stuff, right? We see the layout computers here. There's a root geometry, which is the size of the device. We have the child geometries. And again, this is a simple Hello World app. And the attribute graph looks like this. And this is not the whole thing, right? Like there's stuff all the way to the right. It's massive. And so I don't think, in practice, like after this talk, I hope you're not going to go and like try to explore your own attribute graph for your own app, because for anything that's more than Hello World, it's impossible to read, and I think impossible to reason about. But the underlying mechanism, I think, is very possible to reason about, and so how this stuff works. So, yeah, it's a long answer, and maybe a little bit unsatisfying, but yeah, the short version is, I don't know.
Thank you.
You're welcome.
Speaking of short version, we have one last question, and you have to find a short answer.
Yeah, I think you answered it already indirectly. So what happens if the layout is constrained, like the H stack not having enough space and then the text getting truncated? Is that also happening in a loop?
No, I think the layout algorithm is a little bit different. So what happens with the layout algorithm is it sort of flows in one direction. So the H stack would ask, I actually have a pointer for you there. That's maybe a little bit easier. I will just show you the link and then and very quickly type through it. And then you can see how that works. So the layout is single pass. Let's see if I can drag this here. So this is the SwiftUI field guide. I made this a few years ago. And if you look at the stack example, you can see how the layout system works. So I'll do this very quickly. This typically takes like 20 minutes to step through it, but you can see here how an H stack lays out its subviews. You have like 240 points remaining. That's the constraint. And it tries to measure the flexibility of its subviews. It tries to then order by flexibility. It divides up the remaining space. First, you see the spacing subtracted for the H stack. It divides up the remaining space and steps through that. And it's like a one-way algorithm where there's no loops like with auto layout. It just divides up the space as evenly as possible, and most of the time you get really good layouts because of this. Of course, the example you can see here is something that would be easy to solve in auto layout and not in SwiftUI. In auto layout, the text would be a single line because there's plenty of space available. But that's what this example explains. So if you want to know more about that and how that works efficiently, you could see it on this page.
Oh, thank you.
You're welcome.
All right, give him a round of applause again.
Thank you.